Have you ever stopped to think about how software isn't, well, static? It's always in motion, right? It's constantly changing and reacting to everything we do.
That is a great question, and it brings up a huge challenge for software engineers. I mean, how do you model something that's always in flux? Well, turns out they have a really powerful tool for that exact purpose, a way to map out the dynamic behavior of a system.
And that tool is called the Unified Modeling Language State Diagram, or, UML State Diagram for short. So let's just dive right in and see what this is all about. So here's what we're going to do. First, we'll break down what a state diagram actually is. Then we'll look at the basic building blocks. After that, we'll see one in action with an ATM example. And finally, we'll talk about why this whole thing matters so much for designing good systems. All right, so first things first, what exactly is a state diagram? Think of it like a special kind of flowchart. It's basically a map that shows the entire life of an object in a system. It lays out every possible condition, or state it can be in, and crucially, how it gets from one of those states to the next. Okay, so it's a behavior map for an object. Exactly. You nailed it. It gives developers a crystal clear way to understand and describe how objects are supposed to react to, well, pretty much anything that happens, whether it's a user clicking a button or a signal from another part of the system. Okay, so now that we've got the big picture, let's zoom in on the building blocks. I mean, if this is a map, you gotta know how to read the symbols, right? The most fundamental piece of the puzzle is the state. You can think of a state as just a snapshot in time, a specific condition the object is in. Like for an ATM, it could be idle, just waiting around, or it could be processing a transaction.
Got it. And those arrows connecting them? That's how it changes? Precisely. That's what we call a transition. It's that instantaneous jump from one state to another, from the source state to the target state.
And something has to cause that jump, right? That's the event. An event is the trigger. So for our ATM, you inserting your card, that's the event. Ah, okay. So that's the real power here, isn't it? You're separating the state an object is in from the event that happens and the transition it causes. It creates this super clear step-by-step logic. You totally hit on the key insight. That separation is what stops everything from becoming a tangled mess. It just forces clarity. Okay, so to complete our map legend, we need just a few more symbols. Every diagram has an initial state, that's the starting point, and usually a final state, the end point. And then there are these things called guard conditions, and those are like checkpoints or rules that have to be met before you can move on. Exactly. Think of them as a gatekeeper for a transition. They are absolutely crucial rules. All right, theory's great, but let's see this in the real world. We're going to put it all together with a practical example pretty much everyone knows, an ATM. Whoa, okay, so this is that behavior map you were talking about? This is it? What you're looking at is a map of all the different states an ATM can be in, from just sitting there idle all the way to spitting your card back out. Let's trace what we call the happy path, a totally normal, successful transaction. So the machine starts in the idle state. You walk up and insert your card, that's the event, which moves it to the waiting for PIN state. Then you enter a valid PIN and pick what you want to do. Boom, it transitions to processing. Once that's all done, it moves to ejecting card. Simple, right? Okay, yeah, that makes total sense for a perfect scenario. But, life isn't perfect. What happens when things go wrong? Like, what if I type in the wrong PIN? And that is exactly where our guard conditions come in. Remember the gatekeeper? It's a rule that has to be true for a transition to happen. So, in our ATM example, the big question the guard condition asks is this PIN valid? The system has to get a yes to that question before it's allowed to move on. And here we can see that unhappy path in action. The user enters a bad PIN. So the guard condition, the rule, fails. It's a no. That means the system can't move to the processing state. Instead, the diagram forces it to follow a different path over to the card rejected state. And from there, it ejects the card. And this right here is why these diagrams are so powerful. They make you think through and plan for both success and failure. I get it now. So the real magic here is that it forces developers to think through every single possibility, the good and the bad, before a single line of code is ever written. That's exactly it. That pre-planning is absolutely critical. Yeah, because it's all about translating a simple human goal, like I want to withdraw cash, into a super precise, logical sequence that a machine can actually follow.
What feels like just one simple action to us is, under the hood, a whole series of carefully managed states and transitions for the system.
So, when you boil it all down, state diagrams are just essential for system analysis. They give teams a clear way to model really complex behavior. They help you find those tricky logical flaws way early in the game. And maybe most importantly, they make sure everyone, the developers, the project managers, everyone, is on the exact same page about how the system is supposed to work.
And once you start thinking this way, you kind of see it everywhere. It makes you look at everyday tech totally differently. I mean, just think about your phone right now. Is it locked? Is it charging? Is it connected to Wi-Fi or playing music? It's constantly jumping between dozens of different states, and you could map out every single one of them with a diagram just like the one we saw.